Section 15 of Fires and Firefighters by John Kenlon. This LibriVox recording is in the public domain. Chapter 14. The High Pressure System. The decisive feature governing firefighting in all countries and under all conditions may in every case be summed up in two words: water supply. Personnel may be of the finest, and apparatus of the most complete, but both are helpless if the wherewithal to quench the fires is lacking. Many disastrous conflagrations have owed their magnitude to this circumstance, and it is a curious commentary upon municipal intelligence that many large cities the world over, surrounded as they are with an abundance of water, absolutely lack the means for concentrating it at the scene of a serious outbreak. Small mains, intended for supply under normal circumstances, become practically useless when great fires are in question. Further, fire departments are often criticized by the inexperienced in newspapers and elsewhere for their inability to check a blaze, when the fault really lies with indifferent city fathers who, in their omnipotence, disregard the advice of those who, after all, are paid to know, and absolutely fail to benefit by past bitter experience. During the year 1903, several large fires occurred in New York, and several disastrous ones of great magnitude throughout the United States. The city had been growing steadily, and it was recognized that the water mains were too small to meet an emergency, and the authorities thereupon decided to investigate this most important subject. After careful discussion and consultation with eminent engineers, it was resolved to install the most up-to-date system of water supply known to science, popularly known as the High Pressure Service. In its essentials there is nothing really very remarkable about the idea, and in fact its designation as above is something of a misnomer. As a matter of fact, the actual pressure off a high-pressure main can be equaled by the modern steam fire pump. But whereas the latter is dependent upon the human element in the shape of the fireman who is responsible for the stoking of the engine, and for the quality of the coal and the organization of the fuel supply, and finally for climatic conditions which in extreme circumstances must affect in some degree an unprotected boiler exposed to the fury of the elements, this alternative system is practically independent of all these considerations. Undoubtedly, the ideal situation for such an installation is in a town which draws its water from surrounding mountains, such as in many Swiss cities. It stands to reason that if a reservoir or lake lies some thousands of feet above the point to be supplied, the laws of gravity will ensure a steady and continuous stream of water at any position in the area connected with it at a pressure according to the altitude of the source of supply. The fire departments of Switzerland have shown themselves keenly alive to these natural advantages, and the mechanical fire pump is practically unknown in their fire departments. But, however, the world has not been formed for the convenience of its occupants, and hence it is that science has been compelled to step in and by artificial means to find a solution of the problem. A brief description of the high-pressure system, written from the standpoint of the firefighter, will explain the scheme of operations, and what applies to one city applies to all intents and purposes to others. The service in the borough of Manhattan, the island of Manhattan in the city of New York, protects approximately 2,600 acres. That in the borough of Brooklyn about 1,400 acres, and that at Coney Island about 146 acres. There are 2 pumping stations in Manhattan, with 2,066 hydrants, and some 300,000 feet of mains, chiefly located in the business section of the city. Brooklyn has 1,112 hydrants, including 24 for fireboat connections, while Coney Island possesses 345, including 3 monitor nozzles. In deciding upon the location of pumping stations, prudence naturally directed that they should be placed so as to be practically outside the reach of any possible conflagration, and yet in a position to avail themselves of an unlimited supply of water drawn from either fresh or saltwater sources. Thus the Manhattan stations were located at the northwestern and southern ends of the protected area, the main features of their construction, one-story and basement, fireproof buildings, being almost identical in both cases. These structures are of sufficient size to carry 8 pumping units each, though the present equipment consists of but 6. The contract calls for a delivery from each pump of 3,000 gallons of seawater per minute against a discharge pressure of 300 pounds per square inch, and a suction lift not exceeding 20 feet. At the acceptance tests, the fire pumps in each station totaled a delivery of about 18,000 gallons per minute at the aforesaid pressure, some of the individual pumps discharging as much as 3,800 gallons. This total can of course be increased proportionately, without change in the buildings or mains, by the addition of the 2 pumping units for which space has been provided. Fresh water for each station is supplied through 2 24-inch mains connected with a third of 36 inches diameter. The salt water supply is drawn from the North and East rivers through 2 30-inch pipes. These lead into suction chambers directly in front of each station, and are so constructed that they are at all times below mean low water. This ensures a steady flow, and prevents the possibility of interruption caused by air being admitted to the suction lines. Protection is afforded to the river ends of these mains by heavy bulkhead screens, and to the suction chambers by weighty bronze shields, which are readily accessible for cleaning. The pumping units consist of centrifugal pumps driven by electric motors, both supported on a common bed. Special care as to strength and ability to resist corrosion was expended upon the pumps, which run at a speed of 740 revolutions a minute. They are of the 5-stage type, each stage being designed to give a pressure of 60 pounds to the square inch, or the combined pressure of the 5 stages 300 pounds to the square inch, which is the maximum working pressure of each unit. It may sound a scientific anomaly, but the fact remains that increase of pressure does not correspond to increase in volume. To frame a crude analogy, an ocean greyhound can steam 18 knots at an economical coal consumption. Increase her speed 2 knots, and the consumption of fuel at once increases out of all proportion to the additional speed. Subsequently, each additional knot, or even half knot, will demand an enormous increase in coal consumption, till eventually a certain maximum of speed will have been reached, beyond which it is impossible for the engines to develop sufficient driving energy, no matter how much coal be expended. In other words, thereafter, surplus energy becomes waste. Now, somewhat similarly, each installation of pumps can deliver about 18,000 gallons per minute at a pressure of 300 pounds. But a much greater volume of water can be secured by running them at a lower pressure. Thus, the average pressure required for fire duty is from 125 to 200 pounds at the hydrant, and each station working under these conditions will deliver, with its present complement of pumping units, 30,000 gallons of water per minute. Were this volume of water concentrated within a radius of 500 feet, no imaginable conflagration could survive its attack. The pumping units are set in operation by throwing a switch on the main switchboard, which is directly connected with the motors. By this means the machines are brought into instant use, and in less than 1 minute the maximum pressure can be developed. Current for these motors is furnished locally at 6,600 volts, and each station has 4 separate electrical feeders, 2 from the waterside station and 2 from the nearest substation. Of these 4 feeders, 2 will operate the 6 pumps. but provision is made for connection with the Brooklyn stations of the electric company in that borough, this in cases of emergency. Two 24-inch mains lead out of each station and traverse practically the entire protected area. These are intersected by lateral branch pipes of 12 and 16-inch diameter, which in turn are cross-connected by 20-inch mains at frequent intervals, the water thus traveling only a short distance through a main smaller than 20 inches before reaching the hydrants. These latter are connected to the mains by 8-inch branch pipes, gates being provided at intervals of about 250 feet to enable the carrying out of necessary repairs without affecting any hydrants except those directly adjacent to the gate in question. The pipe system is so planned that without excessive drop in pressure due to friction loss in the mains, it is possible to concentrate 20,000 gallons of water a minute upon the average block of buildings, or the full capacity of both stations upon an area of approximately 1/4 of a square mile. Since the work of the fire department commences at the hydrant, no part of a high-pressure system is more important in determining its efficiency than the type of hydrant employed, which must be ever ready for instant service. Hence, the following points may be tabulated as governing the selection of this most essential feature. Firstly, suitability of design. This includes workmanship and material in order to obtain the maximum of reliable service. Secondly, facility of operation. Thirdly, freedom from frictional resistance to ensure maximum delivery. And fourthly, and of supreme importance, perfect drainage to obviate all possibility of freezing. Without going into a lengthy dissertation upon the specifications prepared and the tests carried out, it is sufficient to say that the hydrants eventually installed are furnished with 4 3-inch outlets, which provide a capacity of 4 2-inch streams with 75 pounds nozzle pressure and roughly 4,000 gallons of water per minute. It was deemed advisable that the main valve in these hydrants, which is 6 inches in diameter, should open downwards against the pressure to be encountered. In order, therefore, that the operation of opening this valve against the heavy pressures liable to be met with in the service mains should be an easy and rapid one, it was so designed that the first 3 turns of the hydrant wrench should open a pilot valve, thereby admitting water to the barrel of the hydrant, thus equalizing the pressures on both sides of the main valve, after which it can be opened without difficulty or resistance. A few seconds is sufficient to accomplish this adjustment of pressures after the application of the wrench. The operation above described sets in action a drip valve, which closes as the main valve is opened, and opens as the latter closes. There is a connection between the drip valve and the sewer, thus ensuring the drainage of the hydrant barrel after use. Valves controlling the hose outlets are provided with a device which balances the pressures, permitting the former to be opened easily with a 5-inch wrench under a pressure of 250 pounds. Needless to say, before this system was finally handed over for practical service in the New York Fire Department, extensive tests were made, 2 of which are particularly worthy of notice. The first took place along the North River front. 21 3-inch lines were stretched from 7 hydrants, and 12 2-inch and 9 1.5-inch nozzles were used. Within 2 minutes after the order to start water had been given, a nozzle pressure of 80 pounds was registered, and so great was the volume of water delivered that the streets speedily became a lake and overflowed towards the docks. The second test was even more exhaustive. 12 3-inch lines with 1.5-inch nozzles, 6 Siamese lines with 2-inch nozzles, a water tower with a 2-inch nozzle, and a deck pipe with a 1 3/4-inch nozzle were all brought instantaneously into action. 1 minute after giving the order to start, a nozzle pressure of 150 pounds was obtained, and in 2 minutes 195 pounds was registered on the 1.5-inch nozzles and 170 pounds on the 2-inch. With the nozzles elevated to an arc of 80 degrees, this pressure carried a solid stream of water 100 feet above the roof of a 14-story building. The gauge on the water tower at this time registered 270 pounds. To the layman, even these simple figures may seem perplexing, so it may be well to translate hard facts into picturesque simile. A stream of water propelled by a pressure of 200 pounds to the square inch, striking an ordinary office partition at right angles at a distance of about 100 feet, would smash it up as though it were so much matchwood, and play with its contents like a whirlwind. Similarly, the same stream, elevated to 80 degrees, could easily clear the cornice of the tallest apartment house in Manhattan, or could wash the dome of St. Paul's Cathedral in London. In 1908, this system was formally turned over to the department, but at the outset the greatest caution was observed over its operation. Thus, companies responding to an alarm in the high-pressure district, as a precautionary measure, always coupled up to the low-pressure hydrants with engines, thus making security doubly sure. As the absolute reliability of the new installation became increasingly apparent, these precautions were gradually withdrawn. Till today, no engines respond to any fires in the high-pressure district unless specially requisitioned. Many outbreaks nowadays are fought and conquered with a second alarm assignment, which, before the advent of the high-pressure system, would have required a fourth alarm, a fact which, trivial perhaps to the lay mind, will be appreciated by chiefs of fire departments in its full significance. No doubt the latter have often realized the danger of having to draw almost every piece of apparatus at their command to a big fire, leaving nothing in reserve with which to tackle another outbreak should one then occur. Simultaneous calls of this nature tax the wit of man to meet, and the days of miracles are past. The first fire can be fought and quelled, but the second, coming when the force is already engaged, forms a very serious menace. In the high-pressure area of New York, 4 fires of some magnitude have been attacked and suppressed at the same time, not to mention several smaller blazes. That fact speaks for itself. Prior to the installation, also, there was always the fear of a sweeping conflagration after the style of Baltimore, but that has passed away forever. New York today is the best fire-protected city on the American continent, but even the knowledge that this is so has not prevented further efforts to meet the demands of the situation. Another pumping station is even now in course of construction, and within 2 years it is confidently expected that the area protected by duplicated high-pressure mains will amount to over 10,000 acres, this in the most congested and most valuable portion of the city. But to return to the detailed description of the apparatus employed in rendering the installation additionally effective. The use of centralized energy for delivering water at a high pressure throughout an entire system naturally entails upon all the mains and hydrants involved the maximum pressure required at any one point. It is therefore quite likely to happen that whereas a pressure of 125 pounds will be ample for one fire, another outbreak may occur in the protected area necessitating a pressure of 250 pounds. This would mean that the pressure would have to be raised suddenly to meet the fresh call, and coming unexpectedly and unheralded, it might seriously endanger the men operating at the smaller outbreak. Or, further to illustrate this point, it is sometimes desirable to take water from a hydrant for a hand line at 75 pounds, and from another outlet to supply a water tower at 225 pounds. To permit of this arrangement, a regulating valve, weighing only 25 pounds, has been invented, which is attached to the hydrant outlet. A pressure gauge is inserted on the hose side, the regulating valve is opened until the gauge needle points to the pressure required, and no matter to what extent the pressure on the receiving side is increased, on the discharging side it remains at the figure selected. If a shutoff nozzle is used on the line, automatically the pressure remains at the figure indicated on the gauge. Even the layman will appreciate the enormous importance of a valve of this nature, without which the system as a whole could not be properly controlled or operated to the best advantage. In order to guard against the somewhat remote possibility of a breakdown of all pumping units in both stations, provision is made for connecting the fire boats of the department to the high-pressure hydrants. By this means these boats can deliver 60,000 gallons of water per minute at a pressure of 250 pounds. In addition, by this method, fire boats may be made to constitute a valuable auxiliary in the case of any great emergency. But as science is never idle and one discovery leads to another, so it is with the business of fire control, and day by day fresh ideas are brought into being, tested, and utilized for the common weal. Thus, in the later portions of the city protected by the high-pressure system, it has been found advantageous to duplicate the mains and hydrants, so that if one set of mains becomes blocked, the other may be brought into service without delay. The system is operated as a unit, but in case of a break in the mains, it can be divided by closing of the motor valves at the selected points. These valves are controlled by switches on the pumping station switchboard, a row of red and a row of green lights indicating the two lines of mains. In the event of a break, pumps are shut down and the motor valves are immediately closed. When the pumps are started again, the pressure building up on the line that is intact will be shown by the colored lights mentioned. The serviceable main will be kept in use at the fire, but the officer in charge must wait about 1 minute in order to see whether the pressure is from the red or the green line. As soon as the pressure shows on either, those lines connected to that disabled will be shifted over to the hydrants on the main intact, and the fight can be continued with ample water supply. During the continuance of a fire, the chief operating can control the pressure of the pumping station, increasing or decreasing the same, or stopping it altogether, by means of a special telephone service run into boxes conveniently situated and specially designed for the purpose, which are plentifully installed throughout the protected area. This system has been found to answer well, though it is open to the possibility that orders may be misunderstood from one cause or another. Probably some improvement thereon may be framed in time as the science of firefighting becomes increasingly popular, and it is better realized what an important part is played by fire control in the daily life of the people. For instance, one of the most gratifying effects of the introduction of the high-pressure system in New York was the immediate drop in insurance rates. In December 1908, about 6 months after this system had been put into regular use, the New York Fire Insurance Exchange made a general reduction of rates throughout the high-pressure zone in Manhattan, a reduction amounting to the respectable sum of $500,000 annually. In Brooklyn, likewise, a reduction of $250,000 followed, so that the improvement has already saved the taxpayer in the community about $750,000 a year. Hence, this method is not one of fire control alone, but becomes positively a good investment. Of course, it may be urged that in the United States the profession of firefighting has developed into such a highly specialized service and has demanded so many drastic changes in equipment and maintenance because the risks incurred are proportionately greater than are met with elsewhere. There is a measure of truth in this, but it is on a par with the individual who, living in a small island, considers motor cars an unnecessary means of transportation and railways a wasteful expense, because he has always found a horse and trap convenient and sufficient for his needs. That is, of course, a somewhat exaggerated simile, but it is an incontrovertible fact that there are many otherwise normal citizens in all the countries of the world who view innovation with suspicion, and shield themselves behind the comfortable assurance that our fathers did very well without all these newfangled notions, and what was good enough for them is good enough for us. This especially as regards municipal outlay on fire protection, though in this respect the writer must lay it on record that New York has always risen to the occasion in the most open-handed manner. For some obscure reason, the average man objects to putting his hand in his pocket for anything in connection with the fire risks of the community, just as much as though he were being held up by a highway robber and willy-nilly had to surrender his purse. There is no advantage in laboring an obvious point, and the writer has in his mind not Europe alone, but some American cities, where the fire department is apparently regarded as a costly and unnecessary adjunct to other municipal offices. Yet in all fairness to those whose responsibility it is to protect the lives and property of those given into their charge, there should be no hesitation in providing them with the most modern and up-to-date apparatus for the discharge of their duties. The mathematical aspect of the whole question, as regards the high-pressure system as a whole, is not a difficult one for fire committees to understand. Since one high-pressure hydrant is the equivalent of 6 engines of the first size, how many hydrants would be equal to the entire pumping outfit of the brigade, using an English term, and would not the initial expense of the installation be more than met by the decrease in personnel, the decrease in insurance rates, and the increase in safety of citizens committed to their charge? The answer to this conundrum should not unduly tax the mental equipment even of one of those corporations addicted to the traditions of the Medes and Persians. End of section 15. Recording by Maria Casper.